In this project, I'm trying to find the value of gravity, g, to the most accurate value possible. Gravity is the force that pulls objects towards each other. The theoretical value for g is 9.8 meters per second squared. The independent variable is the height that the ball is dropped at. The dependent variable is the time it takes for the ball to drop to the floor. The hypothesis is that the measurements will come out to be 9.8 meters per second squared. The equation that will be used in this lab is g equals 2y over t squared, relating height to total time, and lets us find the value of g. The materials needed for this experiment are a meter stick, a ball, and a timer/stopwatch. The meter stick will be used for measuring the height at which the ball is dropped at. The ball is the object that is dropped, and the stopwatch is used to measure the time that the ball takes to drop at the height it was dropped at. To do this experiment, I marked 1.8 meters, which is the height on my wall, using a meter stick, and dropped the ball from that height. I started the timer when the ball was released and stopped the timer when the ball hit the ground. Then I did this 3 times with the same height. I did this for 1.5 meter, 1.2, 0.9, 0.6, and 0.3 meter. Here is the data table for the heights and the different time it took. Distance and average time were inserted using the table before. The gravity was calculated using the formula g equals 2y over t squared. So here are the calculations that I used to find the gravity. I did g equals 2y over t squared, and I did 2 times the height, which for the first one is 0.3, and then I divided it by the average time and squared it, and I got the gravity. So here's the graph for the data, and this is the position time graph with the distance on the y-axis and the time on the x-axis, and as you can see, the graph is not linear. If you look closely, you can see that the points of the dataset are in the shape of a curve or a parabola, and this shows that the linearized graph will be y equals x squared. Here's the linearized data. So for the linearized data, I squared the original times and plotted that, and as you can see, this is a much better fit for the line, and while not perfect, this is due to human error that may have occurred while performing the experiment and collecting the data. If a position graph is curved, the slope will be changing, which also means that the velocity is changing. Changing the velocity implies acceleration. So curvature in a graph means that the object is accelerating, changing velocity and slope. The y-axis is distance and the x-axis is time, making this a position time graph. The percent error for this graph can be found by subtracting the experimental gravity, which is found through the experiment by taking the average of all of the gravities in the data table from before and subtracting it from the actual value being 9.8, and then dividing this by the actual value of 9.8 and multiplying it by 100 to get the percent error of 26.33%. Some errors that may account for why this value differs from the value of gravity being 9.8 is because the timer may have started too early or ended too late, causing the time to be off by a little, leading to the gravity calculated to be different from the actual value of 9.8 meters per second squared. This can be improved by having someone else take the time while I do the experiment of dropping the ball. This will help make the timing more precise and accurate, since I will not be doing 2 things at once. Although the times could have been slightly off, it would not affect g by much. The real reason for why g does not equal 9.8 is because wind resistance acts upon the ball, as we are not operating in a vacuum. While the downward force of gravity acts on the ball, accelerating it, it is also slowed at the same time, hence why the values were close but not equal to 9.8. The relationship between the height, which is the independent variable, and the time, which is the dependent variable, is that as the height increases, the time increases. This is because as the height that the ball is dropped increases, the time it takes for the ball to hit the floor also increases. The linearized relationship between these two is that the height equals the time squared. The graph is a curve and is a position time graph, showing that as the slope will be changing, the velocity is changing. Changing velocity shows acceleration. So curvature in a graph means that the object is accelerating from the gravity.